Welcome back everyone to our second video here in section number 1. This is about the extreme value theorem, and really it's about how do we find absolute minima or maxima, right? And so that's our main objective here, is that we'd like to explore a strategy, try to figure out a technique for finding absolute minimums and maximums, and then of course once we have a technique, well, let's practice using it. Okay, in our last video, right, we saw that closed intervals are good. We want closed intervals, we want continuous functions, and then the extreme value theorem says everything's going to be okay, right? You're going to get a minimum and a maximum, an absolute minimum and maximum. So let's try to figure out, maybe based on a few graphs here, right, where do these minimums and maximums actually occur for these continuous functions on these closed intervals? And maybe if we can figure out this for, a few graphs here, maybe it can help us develop a strategy, right? So, okay, maybe on this first one right here, I can see that the absolute minimum is down here. So this is absolute min. The absolute maximum is up here, right? This is the biggest y value that the function seems to obtain. So I'm going to go ahead, I'm just going to denote abs max, right? Just for some denotation there. So first of all, we saw that the absolute maximum actually occurred at an endpoint. So endpoint. So maybe endpoints are interesting, right? Maybe we need to think about endpoints. This absolute minimum, well, this happened at a jagged edge, right? A jagged edge. This, as we know, this is where derivatives are undefined. So this is maybe derivative, is undefined. So when a derivative is undefined, when you have one of these jagged edges, maybe that's where we can find absolute minimums or maximums, right? You could imagine if this one right here had been a little bit higher, for instance, that maybe this would have been the absolute maximum. Okay, and now let's go over here. We can see that the absolute minimum is again at an endpoint, abs min, and this is an endpoint. So again, endpoints seem to be important. And then the absolute maximum, well, this happens right around here. Absolute maximum seems to happen right around there. Notice something special about the derivative at this one, right? So here we had the derivative was undefined. Here we actually have the derivative is, and if you draw the tangent line, we can clearly see that the derivative is 0. So let's go ahead and say derivative is 0. So the claim is, actually, these are the important issues that will help us figure out where absolute maximums and minimums occur, right? We're not always going to have the graph. Sometimes we're just going to have an equation for the function. And again, this remark here, absolute extremum, so minimums and maximums, seem to appear possibly at endpoints, or where the derivative is 0 or undefined. So in this first case, when the derivative was undefined, we found there was an absolute minimum. Over here, when we figured out the derivative was 0, there happened to be an absolute maximum. So this kind of yields an interesting definition that we may want to make, right? And so this is going to be for a critical, getting ahead of myself here, a critical number. So a critical number of a function f is a number c in the domain, well, yeah, it should be in the domain, such that either the derivative is 0 or the derivative doesn't exist, right? Because those, it turns out, are very interesting for finding absolute minimums and absolute maximums. So let's go ahead and try doing a problem related to critical numbers. So find the critical numbers for this function. So notice that both of these have to do with the derivative. So let's go ahead and calculate out the derivative, f prime of x. So I'm going to get 6x squared minus 6x minus 12. And we want to know when this does not exist, when it's undefined, right? Or when it's 0. Well, what would it take to make this function here not exist, right? Or not defined? Well, that would be things like dividing by 0, taking the square roots of negative numbers, things like this. But in this case, there's nothing that you could plug in for x that would make it undefined, right? So that this derivative doesn't exist. So our only hope for critical numbers is maybe we can find some places where the derivative is equal to 0. So let me go ahead and set this equal to 0. And now I notice that all of these have, let's see, a 6 in them, right? So if I divide through by 6, I would get x squared minus x minus 2. And then on the left-hand side, if I take 0 divided by 6, I'm still going to get 0. And as I promised you guys, really, in the last video, right, a lot of this is going to come down to some algebra, right? So now I'm doing algebra to try to solve this quadratic. So let's go ahead. I think I can factor this one. So in this case, it would be, I believe, x minus 2 and x plus 1. So that means this would be equal to 0 when either x is equal to 2 or when x is equal to negative 1. So I would say the critical numbers are 2 and negative 1, because these are the values that if you plug them into the derivative, they would give out 0. So those are the two critical numbers for this function. All right, so I think we're ready to go ahead and write down a technique or a strategy for finding absolute minimums and maximums. So that's what this theorem is right here, to find an absolute maximum or minimum values for a nice continuous function on a closed interval. Well, the first thing we're going to do is find the values of f at the critical numbers. As we saw, critical numbers where the derivative is 0 or where the derivative is undefined, right? These are important. Sometimes there are minimums and maximums there, right? We're also going to find the values of f at the endpoints. So notice when I'm saying finding the values of f, this is finding the y values, right? Because I'm interested which is the smallest and which is the biggest, right? And so therefore c, the largest of these values in the above, is going to be the maximum value, the absolute maximum value. And the smallest is going to be the absolute minimum value. All right, so now we actually have a technique for finding absolute maximums and minimums. So let's go ahead and try to apply it, right? Now we're moving on to our second objective, getting a little practice using this thing. So here's our first example. I have a nice cubic function, right? X cubed minus 12x plus 1. We have a nice closed interval. We notice that this is nice and continuous, right? We're not dividing by 0. We're not taking any square roots of negatives, right? There's no square roots whatsoever. And we have a nice closed interval. And therefore, we know by the extreme value theorem that we're going to be able to find an absolute maximum and an absolute minimum. The only question is, where are they? So, according to our technique, right, step 1, I want to find the values of f at the critical numbers. Well, darn it, I don't even know what the critical numbers are, right? So let's go ahead and solve for those maybe as our first step. So I'm going to go ahead and take the derivative. 3x squared minus 12, and the derivative of 1 is 0. Okay, and I want to know how can I make this undefined, right, so that the derivative doesn't exist, or make it equal to 0. Well, okay, let's think about undefined. There's no way I can divide by 0. There's no way that I can take square roots of negatives, so this is a pretty boring one. The only hope for critical numbers is when the derivative is equal to 0. So let's go ahead and do this. Let's solve. So 12 equals 3x squared. Divide by 3 on both sides, and I'm going to get x squared is equal to 4. So that means that x is equal to 2, or, right, negative 2. Right? Whenever you take a square root, you have plus or minus. So there are my two critical numbers, right? Negative 2 and positive 2. So I need to figure out the function's value at negative 2, the function's value at 2, and then my function's value at the endpoints, right? The second step is finding the function's value at the endpoints. So in this case, my endpoints are 1 and 4. And actually, you may notice something here, and I chose this example specific because one of these critical numbers, this negative 2, is not actually in our interval. So we don't have to consider this negative 2 because, again, it's not in our interval from 1 to 4. We're interested in finding the absolute maximum minimum on this interval. All right, so let's go ahead and figure out the function's value at these points. So if I plug in 2 into my function, let's see, I'm going to get 8 minus 24 plus 1. And that'll give us negative 15. Okay, if I plug in 1, that'll give us 1 minus 12 plus 1. That'll give us negative 12. And if I plug in 4, let's see, 4 cubed, that's going to be 64, minus 4 times 12, that's going to be 48, plus 1. And that should give us, let's see, 16 plus 1 will be 17. Okay, and then the last step, the largest of these values is the absolute maximum value. The smallest of these is the absolute minimum value. So in this case, negative 15 is the absolute minimum value. So I'll say abs min val here just for shorthand. And then 17, right, this is the largest. This is the absolute maximum value. Now, sometimes I've seen people accidentally write, that the absolute minimum is 2, or the absolute maximum is 4. And this is answering actually a different question, right? This is answering where does the absolute minimum or the absolute maximum occur, right? So the absolute minimum occurs at 2, and the absolute maximum occurs at 4. Right? So you have to be careful. These absolute maximum values, these are y values. These are the things that the function is actually spitting out. So you just have to be a little bit careful when you're answering these things. Okay, let's do one that's a little bit more complicated here. Find the absolute maximum and minimum values for this function, t minus 3t to the 2/3 power on the interval from -1 to 27. Okay, again, we're going to follow the technique, which is, well, let's write down our critical numbers, right? So in order to get our critical numbers, we're going to need to take the derivative. So the derivative of t is going to be 1. The derivative, let's see, I'm going to have this -3 along for the ride. This 2/3 is going to drop down. And then I'm going to get t to the, and I have to reduce my power by 1, right? I'm applying the power rule here. So that's going to be -1/3. So you can see there's going to be a little cancellation. There's 3 on top and 3 on bottom. And actually, let me go ahead and rewrite this, right? Because when you have a negative exponent, this is actually secretly, in the denominator. So let me go ahead and write this as divided by t to the 1/3 power, right? Because now we can see that actually there is a way to make this undefined, right? So again, this is our derivative, and we're interested, right? Where is the derivative undefined? And where is the derivative equal to 0? Because those make up our critical numbers. So I wanted to make sure to give you guys an example of one here that, for instance, if t was equal to 0, so if t equals 0, then we're dividing by 0, and the derivative doesn't make any sense, right? So the derivative is undefined. So therefore, this is a critical number. So therefore, let me go ahead and write down some of what I'm saying, right? The derivative does not exist. So t equals 0 is a critical number. I'll just do crit num. There we go. All right, so we actually have a case where the derivative being undefined occurs. And notice actually that this is in the domain of the original function, right? So the domain of the original function, if you plug in 0, it makes sense because 0 to the positive 2/3, right? That's just going to be 0. So you're going to have 0 minus 0. That's going to make sense. All right, with that hiccup out of the way, pause the video. I'd like to see if you can get the rest of it done. So take 2 minutes, try to finish this one out, and then unpause it, and I'll spoil the surprise. All right, let me go ahead and show you what I've got so far here. So we figured out when the derivative was undefined. That was at 0. So that's going to be a critical number. And then we want to know the other way that we can get critical numbers is when the derivative is equal to 0. So I plugged in 0 everywhere I saw the derivative. And then I went ahead and solved, right? So I moved this to the other side. I did a little cross multiplying, right? So I got this t to the 1/3 up top. And then I wanted just t to the first power. So I had 1/3. And so I raised both sides to the 3rd power, right? So I cubed both sides. And when I did that, t to the 1/3 raised to the 3rd power, remember these things multiply. And so I do get t to the 1st. So 2 cubed, that's going to be 8. So our other critical number here is 8. So now we need to go ahead and find the function's value, well, at the critical numbers, so 0 and 8, and then also at the endpoints, -1 and 27. Notice in this case, both 0 and 8 lie inside of this interval, so you do have to consider both of them. All right, so all that's left is successfully, plugging these things in to our function here. So, okay, if I plug in 0, I'm going to have 0 minus 3, and then 0 to the 2/3 power. So remember, to the 2/3 power, this is that you have to square it, and you have to take the cube root of it, but really the order's up to you. So if I square 0, I get 0, and if I take the cube root of 0, I get 0. So I'm going to have 0 minus 0, which ends up being 0. Okay, how about g of 8? Well, I'm going to have 8 minus 3, and then I have 8 to the 2/3 power. So I have to square it, and I have to take the cube root, but again, remember the order's kind of up to you. So actually, I'd like to go ahead and take the cube root first. So if I take the cube root of 8, that's going to be 2, right? The cube root of 8 is 2, because 2 times 2 times 2 is 8. Okay, and now I have to square that, right? So I have 2, and then we square it, that's going to give me 4. So I'm going to have 8 minus 3 times 4 is 12, and that's going to give me negative 4. G of negative 1. So I'm going to have negative 1 minus 3 times negative 1 to the 2/3 power. So in this case, again, remember I have to square it and I have to take the cube root. The order is really up to you though, so I'm going to go ahead and square it first. When I square negative 1, I get 1. When I take the cube root of 1, I get 1. And so this is going to give me negative 1 minus 3. That's also giving negative 4. And then finally, g of 27. So that's going to give me 27 minus 3 times 27 raised to the 2/3. Again, we're just plugging all of these numbers back into our original function up here, our g function. So again, I need to square this and I need to take the cube root, but again, the order is really up to you. Let me go ahead and take the cube root first. So if I take the cube root of 27, that's going to be 3, right? Because 3 times 3 times 3 is 27. Okay, so I have 3 here. That's already taken the cube root of this, and now I have to square that. So that's going to be 9. So this is going to be 27 minus 3 times 9, which also is 27. So in this case, I also get 0, interestingly enough. So in this case, you can see that the absolute maximum is 0, and actually it occurs in 2 different places. So 0 is the absolute maximum value, abs max value. And negative 4 is the absolute minimum value, absolute minimum value. And again, it actually occurs in 2 different places. All right, and those are the final answers, right? We figured out the absolute maximum and minimum values. Let me go ahead and show you. I actually graphed this one out really quick just so you can kind of visualize again what we're doing here. So here's our nice function, g of t. And again, I'm only graphing it between negative 1 and 27 in this case. So you can see at negative 1, it outputs negative 4. Right? And this is the smallest value around, right? In fact, this is the absolute minimum. And then at 0, kind of our other critical point, right? It has a maximum, right? So this has the maximum, which is 0, right? A height of 0. And then here at 8, we can see that it achieves the absolute minimum again at negative 4. And then way over here at 27, we can see that it actually achieves the absolute maximum again, which is 0 in this case. So there are our, let's see if I click on this, does it actually appear? No. But okay, there is our graph, and that is what we've done. We were able to find the absolute minimum and maximum values without the picture, only using calculus. So this is another application of calculus. All right, that does it for me for this section 1. I'll see you guys next time in section 2.